In this lecture, there's some overlap between section 8.5, which talks about electron configurations based on the element's position in the periodic table, and section 9.1, which takes the topic one step further by defining the terms valence and core electrons. Along with the author's learning outcomes, I've listed a few of our own here just so we're clear of the expectations. Note that section 8.5 will be continued in another video lesson where we discuss anomalous electron configurations and the electron configurations of ions. Let's begin. An electron configuration is a shorthand way to indicate where electrons are located instead of drawing out the energy level diagrams. The goal is to list the orbitals in order of increasing energy using superscripts to show how many electrons are in each orbital. This means we'll use notations like S2, P6, D10, and F14 to denote full subshells. Once you've written out the electron configuration, you'll want to add up all the superscripts to make sure you've accounted for the correct number of electrons. Let's look at an example. Neon has an atomic number of 10, which we used to sketch out the energy level diagram in the last lesson. Using this information, we can write the electron configuration as 1s2, 2s2, 2p6, as shown here. Let's try another example. In our last lesson, we saw that oxygen had 8 electrons to place, leaving the 2p subshell partially filled. If we write out the electron configuration, we'll start with the element symbol, copy down 1s2, then 2s2, since it's the next highest in energy, then 2p4. The periodic table is arranged in order by properties that repeat themselves periodically. These properties are due to the outermost, or valence electrons, which are the only electrons typically involved in bond formation and give rise to an element's chemical properties. Those electrons that are not in the outermost subshells are called core electrons and typically do not participate in bonding. We can look at the periodic table and label it by subshells, S, P, D, and the F block, which is not shown here. We can take it one step further and label each column or group with the expected valence electron configuration. For example, the group 1 alkali metals will always end with NS1 and behave in a chemically similar fashion, while the group 2 alkaline earth metals will end in NS2. The main group elements, namely the S block and P block, all follow the rules this way. We can jump over the D block, for now, to group 17 in the halogens and find their valence electrons are written as NS2 and P5. Example 9.1 from the text essentially asks 3 questions of the elements oxygen, sulfur, selenium, and tellurium. First, let's write out the electron configurations. Now would be a great time to have a periodic table handy. We worked through oxygen in our last example, so I've filled that one out. Sulfur is under oxygen on the periodic table, so pause the video to see if you can write the configuration. Did you get what I have written here for sulfur? Selenium is below oxygen and sulfur, so the configuration is written selenium 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4. Note that if you read the periodic table from left to right, the 3d10 electrons follow naturally between 4s2 and 4p4. Pause the video again to see if you can write the electron configuration for tellurium, which is located in the same column as oxygen. Did you get what I have written here for tellurium? The valence electrons in main group elements are in the highest occupied energy level, or principal quantum number, N. To find this, identify the highest principal quantum numbers, highlight those subshells, and count. For example, in oxygen, the highest principal quantum number is 2. So we'd count the 2 electrons in the 2s subshell and the 4 electrons in the 2p subshell for a total of 6 valence electrons. Pause the video to see if you can count the valence electrons for the rest of the elements. we see that each one of these elements has 6 valence electrons, as I've highlighted here. Finally, the feature that makes oxygen, sulfur, selenium, and tellurium behave in a chemically similar manner is having the same number of valence electrons. Here's another question. Which neutral element has the ground state electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2? If you use the last filled energy level to locate the element on the periodic table, 4s2 indicates the fourth period S block, second column. Go to the periodic table to identify the element in the second column of the S block in the fourth period. We see it's calcium. To write the complete electron configuration for lead, we locate it on the periodic table. Then, reading the table, we get 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, sp2. That was quite the writing exercise. Let's look at a better way to write the electron configurations for elements far down in the periodic table. If we compare the electron configuration for lead to that of the nearest noble gas preceding lead, we see that xenon matches the core electrons of lead exactly. Noble gas symbols are used because noble gases have a completed outer electron shell, and layering electrons outside of this completed shell necessarily makes them core electrons. This shortens the notation for lead to what I've shown here. Now you try one. Write the abbreviated electron configuration for astatine, element 85. Start by using the periodic table to identify the noble gas that precedes astatine, which is xenon. Write the symbol for xenon in brackets, then follow with the electron configuration of the outer electrons: 6s2, 4f14, 5d10, 6p5. As always, I'll leave you with the parting thoughts from the authors. Note that the 8.5 section review part 2 will be included in the next lesson.